you're in your groups. You've got stat.blue open, so you can be resourcing that today. You'll be in the applets page for a little bit, but make sure you get the book open online so you can copy data and paste it into stat.blue for some of what we're going to be doing today. Gets you in the process of then connecting those pieces together. But what you're going to start with in your groups, aside from that, is... Oh, yeah, so I want you to start in section 8.1 of your textbook. And so in a minute, I'll pull it up here in case you somehow haven't been accessing your textbook up until now, which would not be good since we're in chapter 8 already. But if you go to section 8.1 in your textbook, there's an example 8.3 in your online textbook. You're going to need to find the average of the data set for that, and then construct a 98% confidence interval for the true population mean for what are called specific absorption rates. It'll make sense when you read it for cell phones. And assume that the population standard deviation sigma is 0.337. So this is a quick review type question. We've done this a few times already. So go ahead and do that. Remember, in a solution, you're going to have a picture, a formula, numbers inserted, an actual value, and then interpretation of what it means in context. So go ahead and grab that data and make that up quick with your groups. Talk and go. So the most tedious part of this first step was just plugging in all those numbers and dividing by how many? 30, because there were 30. That's a good thing to make note of. That's a very important value. In this problem, as you read through the instructions, like the background information about what is an SAR and that kind of stuff, was there any statement or indication about the shape of the distribution of SARs for all SARs? So as you're reading through that, did they say the parent population this? Or we can assume that the distribution of SARs is this. No, there's not. So there's no statement about parent population, which means I need to make a statement. Since n is 30, the distribution of sample averages is approximately normal because of the CLT, the most important theorem that we will be dealing with in the area of statistics, the central limit theorem. As soon as I have that, that allows me to then say, oh, now I can draw a picture. If I do not make a statement about how I know a distribution is normal, but still draw a normal distribution, there's going to be a major gap in explanation that's going on there. So every time, if you're going to draw a normal curve, you need to explain why you're drawing a normal curve. All right. If the parent population was normal, we could say since the parent population is normal, the sampling distribution of X bars will also be normal. But in this case, there was no such statement about the original distribution of SARs. Therefore, we have to go with the n is 30, which is the central limit theorem. Centered at, so this will be normal. The average will be the average of the X bars. And the standard deviation of this distribution will be sigma sub X bar divided by the square root, oh, sorry, not sigma sub X bar, sigma of X divided by the square root of n. Do we know sigma of, do we know mu of X? Do we know the average? We do not. That's why we're going to be constructing a confidence interval. Do we know the standard deviation of X bars? Yes, we do. It's sigma over root n, which is 0.337 divided by the square root of 30. And did anybody calculate that number out for us? .143. All right. Bobbleheads there in the room agree. Hopefully there's not just one more person. Good. So, and this is also called the standard error. All right. I've said this, that there's sometimes multiple names for the same thing. This is one of those cases. The standard deviation of the sampling distribution is also called the sample error or sampling error. Sorry, it's not sampling, standard error. It's the standard error, SE, standard error. Like that didn't sound right coming out. The sampling standard deviation is the same as the standard error, SE. So we have my justification that it's normal. I have a picture of a normal curve. I know the standard deviation of that normal curve. And then I need to figure out which distribution I'm using. I will use the Z distribution. So clarification, this is actually supposed to be point what? 0.615. All right, so that's my standard error. And because it was a sampling distribution is normal and I know sigma, that's how come I can use the Z distribution. Those are like the two biggies about like, is this a Z distribution scenario? Sampling distribution was normal, central limit theorem. Second thing, sigma is known. When sigma is known, I get to use Z. So my formula will be x bar plus or minus Z times the standard error. My x bar, we calculated out as 1.0237 plus or minus, oh, but I don't know my Z. I'm doing a 98% confidence interval. So my confidence level is 98% or 0.98. Confidence interval will be 98% confidence interval. This down here is 0.01. This down here is 0.01. So then this is where you go to your applet for the normal curve. And in that applet for the normal curve, in the little red box, you're either going to put 0.01 or 0.99, depending on if you have it as like greater than a value, you put 0.01. If you had it as less than a value, it'd be 0.99. 0.99 because it's the 0.98 plus the little bit at the end. But I really need to find whatever the z-score is for 0.01 as a small tail. And I see some of you on your screens have that up and running. What is my z value? Anybody at all? So on the applet, you want mu is 0. The standard deviation is 1. Sigma is 1. Because that's a standard normal curve, 0 and 1. Then you put in the 0.01, and you get a z-score of 2.326. Now, if you're not getting that number, check with someone near you. Have me come over to see if you're getting it set up right. Because, again, these are just technology tools that keep you from having to look up a whole bunch of table of values all the time. Knowing how to use the tool in context with what the situation is that the problem is, that's where just more and more practice will help. The standard error, that was the sigma, that's a square root symbol. Sigma over the square root of n is the standard error, and we calculated that out to be 0.0615. So you get to that place, and then you do 1.0237 plus those things multiplied, and then 1.0237 minus those two. If you've not done that, go ahead and calculate those out now. So then I get those two values. Hopefully someone else is calculating it and got the same number. If not, then either you made a mistake or they made a mistake. And at this point, you might think, wow, I'm done. Except that every time, let me emphasize this, every time a problem asks you or I ask you to construct a confidence interval, even though I might not say it, and I probably won't say it, you must include an interpretation of what that means in context. I would say something along the lines of, I am 98% confident that the true average of specific absorption rates for all individuals in this population will be between 0.8807 and 1.1667. And if they gave me units, I'd throw my units on there too. I would not say there is a 98% chance that the average specific absorption rate is in this interval. And state those numbers. Because it is not a probability. The second way that I could explain this in context that would be a correct interpretation of a confidence interval was if I would repeat this process over and over and over and over and over again, thousands of times, I would expect 98% of the confidence intervals that I created would include the actual average specific absorption rate for cell phones. Those would be the two ways that you could correctly interpret this confidence interval. So then here is just kind of what we just did. So when we calculate the sample mean. So we remember in this section, we already know the population standard deviation sigma. That was important. And then that allowed us to say, therefore, use Z distribution. All right. We found the Z-score that corresponds to the confidence level we were looking at. We used that. We used an applet to do that. Then we calculated the standard, or what our book calls the EBM, the error. I forgot the word, the M letter on there. It's the error bound, which is the margin of error. Margin of error is equal to Z times the standard error. Then we constructed the confidence interval. We wrote a sentence that explains that estimate, and that explanation includes context for the question. So now, we're going to go and take this a little bit further in this step. The population standard deviation for the height of school basketball players is 3 inches. That's sigma. I know sigma. That's an important thing. The question then goes, if you want to be 95% confident that the sample mean height is within 1 inch, when a statement like that gets made, what they're talking about is they want the margin of error to be within 1 inch. And realistically, the better thing should be, they want the margin of error to be less than or equal to 1 inch. If it's better than 1 inch, then you're within 1 inch. If it's just over 1 inch, you're not within 1 inch. If you're exactly at 1 inch, then obviously, okay. So what you're going to do is take some time thinking about the formulas that we've used so far, which hasn't been that many for standard deviation, for confidence intervals. In your groups, see if you can figure out how to solve this question. That is, so if you know you want to be within 1 inch, how many people do you have to sample to guarantee that that's going to happen? All right? I'll let you begin the struggle now. So as I said, even though it's not stated here, I will tell you now. I should have written it in there. You can assume that the heights of basketball players are normally distributed. That's an important piece of information here because If there's a normal distribution, that means the sampling distribution is guaranteed to be normal. And sigma is known, so we are using the z distribution. Did anybody find n? Yes, sir. What do you get?
I got
24.345. Okay, and it would be n greater than or equal to, which means I would have to have n is equal to 25, because that's the next nearest integer greater than 24. For those of you that have ever done pre-calc and calc, when you did the greatest integer function, you're like, when am I ever going to use this in an actual event? Ta-da! Here it is. If you don't know what I'm talking about, then is what it is. All right. If you're wondering about where that came from, what is the margin of error formula? Margin of error formula. So when we're doing a confidence interval, it's x bar plus or minus the margin of error, which means the margin of error is equal to z times the standard error, because that's what this is over here, z times the standard error. Specifically to what we're working on in this problem, the standard error is sigma over the square root of n. So this could then be rewritten as z times sigma over the square root of n. And I want my margin of error to be less than or equal to 1. Some of you might be seeing like, oh, wait, I think I know what to do next. That's right, we draw a picture. 95%. That's my confidence interval that I'm looking for, which means this tail is 0.025 or 2.5%. 95% middle, 5% total on the ends, split evenly, 2.5%. Go to my applet for a standard normal curve. 0 is the mean, 1 as the standard deviation. Plug into the little red box in the applet, 0.025, and it kicks out a number of 1.95996 maybe? 6. That's my z. That goes right here. I know sigma. It was given to me, and it is 3 inches. That goes right there. So then I have 1.95996 times 3 over the square root of n, less than or equal to 1. Now it's algebra. Multiply both sides by the square root of n. I'll have 3 times 1.95996 equals the square root of n. If we both multiply both sides by the square root of n, that's moved it over out of the denominator. And then I will square both sides. So I'm going to take all of this and square it, resulting in n being 24.345.
I messed up on the z-score.
So someone messed up on the z-score, so this is not the correct number. Nope, it does not. The question is, does it have to be over 30? No, because I told you, and I should have written it up here, you can assume the heights of basketball players is normally distributed. If you can assume that the population is normal, I can do a sample size of 2, and the sampling distribution will be normal. I can do a sampling size of pretty much anything, because the original distribution is normal. The only time I need 30 is if I do not know the shape of the original distribution, or if I know the original distribution's like skewed, then I got to make sure I have at least 30 in my sample size. So what should the n be? 3 times 1.95996, take that answer and square it, and we get a number that is, what's the number?
35.
What is it without rounding? 34.57. So n would have to be 35 because that's the next integer. So I'd have to sample, if I wanted to be within 1 inch, so I have an interval that's only 2 inches wide. So if I'm within 1 inch, that means my interval width is 2 inches wide. So a 2-inch wide guess for the actual average height of high school basketball players, I would have to sample at least 35 individuals to have an interval no more than 1 inch margin of error, which also means no more than a 2-inch wide interval. I say that because sometimes your book, and sometimes myself, will make it somewhat confusing by saying if I want an interval to only be 2 inches wide, well, that right there means the margin of error is only 1. If I want an interval to only be 5 inches wide, then I'd have to have a margin of error of 2.5 inches. So that's how I get at, do you understand the difference between interval width and margin of error? Or in this case, margin of error versus standard error, where the z-score goes in. So when we don't know sigma, we covered this last time, we're going to do it again. First thing first, we always have to know that there was a random sample. Was it a simple random sample or a random sample of some kind? 2, either the population we were told or was assumed to be normally distributed, or the sample size is over 30. If that's the case, then the sampling, so if one of those is true, so if one of those is true, then the sampling distribution of x bars is approximately normal. It's a great phrase to make sure you're using often in your writing and your solutions. If it's true. Don't use it if it's not true. If sigma is not known, when that happens, then we use what's called the student's t-distribution. And my formula changes slightly. Instead of x bar plus or minus z times the standard error, it's x bar plus or minus t times the standard error. And our degrees of freedom is n minus 1. That's important when we look at a t-table or use the online applet for finding a t. Degrees of freedom is, if you really want an explanation, I can tell it to you later. But for the scope of this class, just memorize it's n minus 1, and you'll be good enough. Because, well, then we go to here. So we're going to kind of walk through this quickly, showing you most of the work that goes into this. So don't be copying a lot of this down, but look at it. Before I go to the next slide, I'll pause. So if you have questions, you can pause and get a question. Because the next slide, I'm going to insert a lot of the information into the table and things. So if you do a study of hypnotherapy, that's right. Does hypnotics actually improve your sleeping habits? All right. To find out, does it increase? There we go. Does it increase the number of hours of sleep a subject gets each night? You measure hours of sleep for 12 subjects selected at random. I'll tell you that right now. With the following results. We're going to construct a 90% confidence interval for the mean number of hours slept for the population, and we can assume the population is normal, from which we took the data. And here's my data set. I'm going to quickly walk through how we calculated standard deviation again, because we haven't done that in a long time. You're not going to have to recreate this, but it helps you appreciate what's going on when we talk about what is standard deviation. I would say most people who get out there in the business world, they see standard deviation, they go, oh, that's a big number. It must mean it's really spread out, and it all depends on context. All right, and this is coming from section 8.2. So if you have your books open, you can go to 8.2. Section 8.2, we're going to go down to the try it 8.8. That's where this data is that you'll be able to select with your computer, and then we're going to paste it into Stat Blue in a second, but don't go there yet. You can go to the 8.8, the try it 8.8 on section 8.2 to get this data. But what I'm going to do is in this, I took each of those values and subtract it from the mean. And the mean for that data set, we should just write this down here, I guess, somewhere. My X bar for this data set was 8.9833. That was the average. So if I take every data point, these are each of the data points, subtract it from the mean, so X minus the mean, it tells me these values. These are just what you would call deviations. Not a standard, these are just deviations, which outside of rounding, they're gonna always add to 0. Because your data set will always be equally dispersed above and below the mean, because that's a characteristic of the mean. It's the average of them. So if you find out every data point's distance from the mean, that's all their distances from the mean, some are positive and negative, add them up, they add to 0. But anyways, what I do is I take those, I square them, and then I add them all up. Down here, there's the sum of them, because this is the formula for the standard deviation. Each data point minus x bar squared, add them all up, and divide by n minus 1. Just like the degrees of freedom in a t, it's the same idea for why this is n minus 1 and degrees of freedom is n minus 1. There's that number, and then this will give me what the s value is, which we'll actually see on the next screen. But what I want you to do now is to go ahead and open up StatBlue, if you don't already have it there. And as we look at StatBlue, we've spent a lot of time right here in one variable, descriptive statistics. We did histograms, we found values, there was a box plot, we found averages and standard deviations, mins, max, all of our quartiles there. Now we're gonna go to this column, inference for population means. One sample T confidence interval. That's what we're doing next. So go ahead and click on that button. And when you do, it takes you to here. Here, not this. It takes you to here. One sample T confidence interval. If you go to that section 8.2, the try it 8.8, and just highlight the data, and then if you're an Apple user, it's Command C. If you're not an Apple user, it's Control C. It's the same thing to copy it. If you go into this column, click in it and hit Command V or Control V, it'll paste that data right in there. And if it has the semicolons, that doesn't matter. The computer is smart enough to know that that's not a number. It's a way to distinguish one point from another point. But it'll insert all those data points in there. What you're going to do then is change the confidence interval to 90. And then when you're ready, hit calculate. So once you do that, you get this output. N is 12. It even tells me degrees of freedom is n minus 1. Yay. It tells me the square root of n. It tells me x bar, which we already had from the previous side. It tells me s. What it does not tell me is it does not tell me the standard error. The standard error in a t distribution is s over the square root of n. In a z distribution, it was sigma over root n. See the similarities? Sigma, standard deviation of population, s, standard deviation of a sample. So you will have to figure that out by formula for a t interval. I'll do it right up here, is going to be, that's not what I wanted to draw, x bar plus or minus t times s over the square root of n. I could have also written x bar plus or minus t times the standard error of the standard error. Those are the same thing. I find many people like to write it like this because then you're keeping track of the s over root n and not having to memorize, wait, what's the standard error? Now, if a question tells you the standard error, then you're going to have to know, oh, that actually means s over root n. So you're going to have to find that. So in a case like this, where like, oh, the computer, quote unquote, does it all for me, it doesn't. The first thing that you had to do is look at the information and say, the original population was normal, therefore my sampling distribution is normal, and you would say a statement like that. Second thing, you would say sigma is not known, so we're going to have to use s. And when my sampling distribution is normal and I'm using s, therefore I use the t distribution. Then you're going to plug the data in here to find the standard error. This t value, this critical value, so if I were to draw my t distribution, it's like a little bit wider than a z. My t distribution, centered at 0, just like the standard, just like the normal curve, the standard normal curve, the z distribution centered at 0, so is the t. That critical value, 1.79, 59. And right here, negative 1.7959. Those are the endpoints of a 90% confidence interval for t. Which means this number is the number that goes into that part of the confidence interval. X bar, which we were told here, that goes in here. And then these two numbers that I combine will go here for my standard error. Now I've got the table on there. The reason why I have the table on there is don't be surprised on the exam for a t-distribution for me to say, and on this little excerpt of the t-distribution, find the correct critical value for a certain type of a scenario. So in this case, we were doing a 90% confidence interval. The t-distribution actually has the confidence intervals at the bottom, 90% on the table. Or you can look across the top and say, well, 90% here means 10% is left over, which means this end is 5%, and this end is 5%. So if I'm looking at a one-tailed, that would be, I gotta take my glasses off and look, versus two tails. So two tails is 10%, one tail is 5%, right? One tail is 5%, but the two tails together is 10%. Corresponds with the same column as 90%. So that's my column I'm looking at. My degrees of freedom are 11 because it's n minus 1. And I go across to right here, 1.796, which is the value that the computer kicks out at you anyways. Showing you that's where this number comes from. That's where you find it on your table. And then the last thing I would like to point out that you should really pay attention to is whoever designed this applet did an extremely poor, or I should say, a great example of how never to write a conclusion about a confidence interval. Because what he wrote is mathematically wrong. And I know it's a he, Bogner, I think it's Michael. Anyways, they say there is a 90% chance that the true population proportion lies somewhere between here and here. That would be wrong. That would be a wrong statement. That is, it's not a chance. It's not a probability. Technically, it's binomial. It's either in it or it's not. So there's not a probability of it being in that interval. It either is or isn't. Now, if I made 100,000 intervals. So this would be the only way you could get around the chance idea or probability idea, but this is kind of an obtuse way of approaching this problem. But if you did 100,000 samples and you made a confidence interval for all of them, and let's say you had all of those confidence intervals written on a little piece of paper, folded up and put into a hat, right? So you got 10,000 slips of paper, each of them, no more than that, 100,000 slips of paper, each of them with a confidence interval written on it. All right? We expect 90% of them to have the true mean because it's a 90% confidence interval. So I've got 100,000 of them in this hat. I shake up the hat, I reach in. What is the probability that I'm going to pull out one slip of paper that has an interval that does include the sample, the true mean? That would be a 90% probability. Now, you take it out and you look at it, you still wouldn't know if it actually includes it, but that's how you would make this into a probability scenario. Again, that's a very obtuse way to try to approach interpreting a confidence interval, which is why I will say it, but never expect you to have to be able to answer that question. Instead, we say, I am 90% confident that the true average, what's my context? Do I have it here? There it is. So here's the two ways to interpret. With repeated sampling, we'd expect that 90% of the intervals constructed to find the average amount of sleep with hypnotherapy would contain the true mean. All right, I got hypnotherapy in there. I've got something that implies context. I think this is a easier way to remember how to interpret a confidence interval by saying I'm 90% confident that the actual average number of hours slept with hypnotherapy is somewhere between 8.314 hours and 9.65 hours. The third type of confidence interval that we're doing in chapter 8 is for a scenario that's going to be starting out looking an awful lot like a binomial. If you remember back to the binomial, a binomial is a case where there's only one of two outcomes. The probability of success for any individual outcome is constant. Every individual occurrence is independent of all previous occurrences. And there's a finite number of trials. That was a binomial. Those were the conditions of a binomial. So what we find out, so this, if that's true, then X is approximately a binomial when there's n number of trials and P is the probability of success. If n times P is at least 5 and n times Q, that means there's at least 5 successes and 5 failures. Q is 1 minus P. So if there's at least 5 successes and at least 5 failures in whatever sample I'm doing of people, of things, of events, that are either they are something or they aren't something, then it will follow a normal distribution with an average of NP and a standard deviation of square root of NPQ. So that would be the entire population. When we're estimating X, we would call it X bar. Instead of a mu, we would say it's X bar. Instead of P, a probability proportion, we're now going to say P hat. So introducing a new little nugget of information here. So P hat is a sampling proportion. You'll see what that looks like in a problem that we're going to do on the next slide. But P hat is a sampling proportion. X bar, sample average. P hat, sampling proportion. If this is true, NP and NQ are both at least 5. That means there's at least 5 successes, at least 5 failures. Then the distribution of P hats is normal. And the average is NP over N and square root of NPQ over N. Because see what they did is there's NP, there's square root of NPQ. Well, if I do a sample of size N, the N's reduce, I'm left with P, and then PQ over N. But let's see what this looks like in action. Suppose that market research from a firm is hired to estimate the percent of adults living in a large city who have cell phones. Okay, granted, this was done a little while ago, so the actual numbers here are lower than what you would expect, because now, I mean, everybody qualifies for a cell phone. Seems like, of course, except for middle school kids, right? They always complain. Everybody else has a cell phone, to which I would respond to my children, no, they don't. Yeah, they do. I said, no, they don't, because you don't have one. So therefore, everybody does not have a cell phone. Yes, I was that dad. Shocks not many of you, does it? So, of the 500 people surveyed, 420 responded yes. So that means, let's see, so my P hat is my sample proportion of successes. 421 out of 500. My Q hat will be those that are remaining. 79 out of 500. My N was my sample size, which is 500. And a 95% confidence interval. So before I can do that, I have to find out, is this approximately normal? Apologize on that, I just can't spell. Normal. Here's what I do. There are 421, which is greater than or equal to 5 successes. 79, which is greater than or equal to 5 failures. Therefore, P hat distribution is approximately normal. Lots of words and sentences, but that is one of the linchpins to being able to do this problem. If I don't say that, then I can't do a normal curve. But as soon as I said that, now I can do a normal curve. Z, 95%. And we've done 95% a few times. 1.9699, sorry, 1.95996. There we go. So that is the z-score for a 95% confidence level. You're going to find out that the most common ones are going to be 90%, that's 1.28 and change. 95%, 1.96, which is rounded from 1.95996. 99%, 2.75. So you're going to have some of your more common z values that go for that. And how we're going to use that? Oh, this formula. P hat plus or minus z, because we said it's a normal curve, times the standard error of p hat, which is pq over n square rooted. So when you've looked at that formula chart, a card that we had that you'll see again, the confidence interval is statistic plus or minus critical value times standard deviation of the statistic. But then every time, if it's x bar, then this is sigma sub x bar. If this is p hat, then it's sigma sub p hat, or standard error of the p hats. With inaction. Oh, no, we're going to do the other way around. P hat plus or minus z times pq over n square rooted. This would be like we did with the other one for finding n. I want to be within 3%, which means I want this to be less than or equal to 0.03. My z is 1.95996. My p and my q were 421 over 500 times 79 over 500 divided by n. If that were the case there. If I have no idea about these two values, in some cases that's true, we would assume there's no difference and it'd be just 50-50. That was a quick thing right here at the end as we close up our time. We're going to be hitting more on this one when we come back on our next time together. So until then, keep working on all those check your understanding problems.